Hi everyone and welcome to a new video about control system topics, and in this video we will discuss the analytical design of PID controllers, and this is our example number 1. In this example I will give a brief introduction about the concept of analytical design of PID controllers, and we will look at an example of a design of a PD controller. Now, as we did in the previous videos, we will look at calculations and we will verify all calculations using simulations in MATLAB. So let's look at the situation. Introduction to analytical controller design. So we have an analysis that looks actually to the dominant closed loop pole. So we use the location of the dominant closed loop poles. You can have a system, of course, with the number of poles and zeros, but what we use is in fact an approximation. Take the dominant closed loop poles, and based on that we will carry out our analysis. So now we denote one of the dominant closed loop poles as S1. So there are of course two closed loop poles dominant because they make a pair, and we take only one of them and carry out the calculations using this one of the poles. Now, the dominant pole, we call this S1, is in general actually a complex number, so it has a real part and an imaginary part. We will see that shortly. And now the dominant pole S1 is also written actually in angle beta, so which is actually shown here. So there is an S1, which is given as a magnitude, which has some vector, so it is a length, and it has also its associated phase. Now, in addition, you have also the loop gain or loop transfer function LS, and which is also written in its magnitude and also in an associated angle, which is shown here as alpha. So we have an LS, which has a length, the absolute value of L, and we have the angle e to the power j alpha. Now, the design equations for PID controller using analytical method are the following. So let's look at first what a PID controller is, and briefly. Now we have the P controller branch, which is just an amplification, linear amplification. You have the integral part, so you have the integration, and associated with that its own gain. And we have the derivative part, derivative branch, and we have also its associated gain. So if you combine these three branches together, you will have the PID controller what we know as a classical PID controller. Now this is in time domain. If you convert this to the Laplace domain, the S domain, then you will have this expression. So this is most time used in analysis. So the PID controller is then given as a transfer function as shown here. So we have the controller, which is given as Kp, which is the proportional controller gain, and Ki divided by S, which is the Laplace expression for the integral control, pure integral control, and then plus Kd of Kd times S, which is the pure derivative control. Now the parameters which you see here are three parameters, Kp, Ki, and Kd, which is actually shown here. We will determine those three also depending on, of course, the analysis. If you want, of course, Pd or Pi, you will, of course, don't need one of these three parameters. Now these are the equations. I won't drive these equations. This is just what we have. So we will use this in the examples. Now the Kp, which shown here is the proportional controller gain, depends on alpha, beta, and also the length of the loop transfer function, also the length of this dominant, or one of the dominant pole we have chosen. Now this is also for the Kd valid. We also need, as you can show here, the value of Ki. I will come back to that shortly. And in symbol form you need the alpha, beta, and also the length of the S1 and also the loop transfer function evaluated as S1. So if I now look at the equations, we have three unknowns, the Kp, Ki, and Kd, but we have two unique solutions. So that means we need to choose one of these three parameters. So we cannot make a unique solution about this. So we can select one of the unknowns and calculate the other two unknowns using the selected value. So most of the time we will select Ki specified to achieve a desired steady state error. So we need, for example, a steady state error of 0, then the Ki can be taken some number, not too small, because that will of course make the response very slow. If you take it too large, maybe the other parameters will be also too large or too small, which will not be practical. So that will also depend on the application. Now, the design equation can also be used to design a PI or PD controllers by setting the appropriate gain to 0. So, as we said before, if you want, for example, a PI controller, you will set just KD to 0. So this branch is actually not interesting for you. But if you want a PD controller, then you will set actually this branch open. That means actually your KI will be 0. So that's actually very straightforward. This is an important note. The above equations, the design equation we have discussed, can be only used for a pole which is complex. So we need a real part and an imaginary part. Now, for the case that there's only a real, it's possible, then the 0 of the PD controller and the 0 of the PI controller are actually specified also, and the corresponding gains to satisfy the angle and the magnitude criteria are obtained accordingly. So this is a note I just put here. We won't go too much in detail in this part, so we will see that the S1 is most of the time just a complex number with a real part and an imaginary part. Alright, now the parameters again, KP, KI and KD, these are very important. So let's look at an example that is of course important. We will now design a PD controller using the analytical method. Now, this is the configuration. This is actually the diagram we have here. So we have the controller G of C, we have the plant G of P, and we have the unity gain feedback, negative feedback configuration. Now this is the transfer function for the plant, 1 over S times S plus 2. And we have also the controller, which is shown here as the PD controller with the P controller gain and the D controller gain. Now, design specifications, this is just a design. We need an overshoot MP less than 4.32%, and we would like to have settling time with a 2% criterion of 2 seconds or less. So less than 2 seconds. Okay. So what is the solution in this case? Now, before we start, we need to know what we do with these specifications. So if I look at the overshoot, which is of course given as a specification 0.042432 actually here, but it is approximately the same. If I want to convert this to the parameters I can use in a complex plane, I need the damping ratio. Now, the damping ratio is related to the overshoot in the pure second order system using this formula. So you can rewrite this and you can get also from the zeta the overshoot, but this is now from the overshoot you will get the zeta. So if you just substitute the value of MP in this formula, as you can show here, you will get 0.707. That's actually what we have for the zeta. Now if you also carry out the calculation for your settling time, it must be less than 2 seconds, so I will make it exactly 2 seconds in this analysis. What you have is a TS, which is the settling time, is actually equal to 4 over the absolute damping. Now, so the absolute damping, sigma, is 4 over the settling time, so it's 4 over 2 is just 2 radians per second. So this one is interesting because that's also the real part of our S1, which is actually our design point. Now, I also want my imaginary part, which is given by the omega d, and omega d is equal to the sigma times the cosine, the tangent of the cosine of the damping ratio. So I will first need to determine the zeta, the damping ratio, and then take the cosine of that one, and also take then the tangent of that result. So that is then given as omega, and omega d actually here is given by 2 times the tangent of the cosine of the zeta, which is exactly 2. So we have a 2 for the real part and 2 for the imaginary part. Those are all given in radians per second as a unit. So from these values, the closed loop poles can be determined as S1 or S2 as sigma plus or minus j omega d. And omega d is called damped frequency. So this is then S1, 2 is then minus 2 plus or minus J2. And I will of course take one of these. So I will take the positive with the positive sign for the imaginary part. So we start with the P controller. That's actually the way to start. So we will make our controller here just P controller, but we will also make it just one. So very simple, just this is just a line here. So, and we will take the S1 as -2 plus J2. So as our input for the design equations. Then we have the following situation. So S1, which is now given of course then in the magnitude and the phase, the magnitude here, S1, is calculated as follows. So we have the S1 is equal to the length of this vector. So it is the square root of -2 squared plus 2 squared, so -2 between the parentheses. You will get the square root of 8. And the phase associated with this one, if you draw this on the complex plane, I've done this in another video in more details. You could look at it also. You need to have 180 degrees plus an arctangent of the imaginary part divided by the real part. That will give you exactly 135 degrees. So if you have the angle and you have also the length, and have your S1 is equal to the square root of 8 times e to the power j 135 degrees. This is for the first part of the design equation. Now for the second part, I will also look at this graph. For example, this one, beta, this is actually this angle, which you show here from the origin all the way to the design point S1, as you can show here. So we have -2 for the real part, J2 for the imaginary part, and you can see that this angle, which of course is measured from the positive real axis, that is actually our reference. And the length of this is actually just the length of this vector, so it is actually using the length here and the length there. So that's actually what we have here from this analysis. Now the next equation is actually using the loop transfer function, and we evaluate the loop transfer function at S1. So you substitute the value of S1 in there, and you will calculate the magnitude and also its associated angle. Now what is the loop gain or loop transfer function? You will make here in this diagram a full circle, and that is actually a loop transfer function. That will be the controller times the plant times 1, which is just the controller times plant. So it's just the controller times plant. Now since the controller is taken here as 1, we have then 1 times the plant transfer function. Now then the next step is, what is then the associated angle alpha in here? Now the alpha, it's shown here as -90 degrees plus -135 degrees, which is then in total -225 degrees. Why? Now if you look at the two poles, which is at 0 and at -2, which is at 0, it is -2, you will need to calculate actually how much phase contribution you have if you look at this point from the two poles. Now since it is a pole, you will have a negative phase contribution. If it is a 0, you will have a positive phase contribution. You already see a 0 here. This will be discussed shortly because this is needed when we have the PD controller. So if I look only at the two poles, which is actually due to this plant, I have a phase here is exactly the same as this one, is -135 degrees, but since it is a pole, I have to make it negative. And this one make actually here from the -2 position, the location of the second pole, makes a right angle if you look at the S1, so it will contribute -90 degrees. Now if you combine them, you will get this result. So it is -225 degrees for alpha. Now if I also look at the length of this, because I also need the length, I just substitute the value of S1 in here. So S1 is this number, so S1 in here, also in here. And if you do the math here by calculating the length of this part, calculating the length of that part, and then 1 over the two lengths multiplied, you will have the square root of 8 times square root of 4 here, because it is 0 as the real part and the imaginary part is just 2. You will have this expression. And we already know the alpha, so if I substitute this here, so this is actually this one, this is the length of my loop transfer function, and this is the phase here what we have for alpha, then we have the following expression in a simplified form. So we have now the expression for the S1, which is shown here, and we have the expression for the L1, we have also its associated lengths. We need that in the design equations shortly. So we will use Ki is equal to 0 because we design a PD controller. Then the design equations are the following. So Kp, which was this expression, Now I take the alpha, beta, and the length of the loop transfer function at S1, and also the length of the design point, and I substitute it in here, and I will have the value of 8. So my KP, if you do the math here, you just calculate out this expression, you will have exactly 8. Now, you also need the derivative controller part, so that the KD, exactly the same expression for the design equation. Yeah, you will substitute the values, you will have exactly 2. If you combine those two in the controller expression, which is G of C, KP plus KD of S, then we have actually 8 plus 2S. So we have the 8 for the KP, we have the 2 for the KD. If you write this down in a little bit different form, you will see directly there is 2 times S plus 4. And then in this case, you will see that there is a 0 at minus 4, and which is actually this 0. And that will contribute actually 45 degrees. So let's look at the simulation result using this. So we have now the unit step response of the closed-loop system with the PD controller with 2S plus 8, which is actually 2 times S plus 4. This is actually our controller. Now let's look at the unit step response. What you see is the following. We have now the plot of the unit step response. I have just called this T as the total system. And I see that the settling time is 1.86 seconds. So it is less than 2 seconds, that is okay. But I see that the overshoot is 6.7%, which is larger than actually what I wanted, which is maximum 4.32%. So this is not what I wanted. The final value is 0, well, I mean 1, so it is 0 steady state error. The rise time is approximately 560 milliseconds. But the thing is, the overshoot is not what we want. It's too much. So we need to adjust this. So you see, it is larger than 4.32. Actually, it's not 23, but 32%. So it is larger. So we need to adjust this. So what we can do is, there are many ways to adjust this. We can of course work on the controller because the plant is fixed, so we cannot change the plant in this case. So you can change maybe the gain of the controller or maybe the location of the 0. We will see how we can tackle this. Let's look at it in the next slide. So we have now the unit step response of the closed loop system, but then with the adjusted PD controller. What I have done is actually the following. I have just keep the value of the controller, P controller, as 8, but I made the D controller, I changed it from 2.5, from 2 to 2.5. That will result in 2.5 times S plus 3.2. That means the 0 is now moved from, in this case, from minus 4 to minus 3.2. That's actually what it is. So I have moved the 0 from minus 4 to minus 3.2. That's actually what you see here. And this is a unit step response, and I have just called it T1. So what you see here is that the overshoot is 4%, approximately 4.01, which is less than actually what is maximum allowed. And we have the settling time of 1.74 seconds. It is also smaller than what we had before, and it is definitely smaller than 2 seconds. So in this form, the design is actually completed with this controller, with the PD controller in this case. So we have to make the adjustment, a little bit adjustment, by making the D controller gain larger, and that makes the 0 of the PD controller smaller, or makes it closer to the vertical axis. You might ask, can I make this maybe larger or smaller, or maybe this smaller? That is actually what you need to simulate and also judge for yourself what is the best option. This is not a perfect solution. This is one of the solutions to make actually the specifications and their results come close to each other. So I've chosen this to analyze actually the situation. So in this case, I have the design completed by making a small adjustment in the D controller gain. Okay, this is just for the PD controller. I will do that in another video, in a second video about the PID controller specifically. Then we will see what we have there, and maybe we also need to make an adjustment in the controller. So I will see you next time, and if you have questions or comments, please let me know, and take care.